with GANs. I joined ING at the beginning of 2020 in February at Wholesale Banking Advanced Analytics team, and I teamed up with Fabian Janse and I did my master research there for Maastricht University, and I will go through the research that I've done at the university. So this really is a research project, and I'm excited to walk you through it. So let me first introduce what we have done, what the problem was. So I think some of you are familiar with generative adversarial networks, which is a machine learning algorithm that is able to generate synthetic images. Mostly, it is mostly used in image generation or video generation, and also known as deep fake images. And let me just give a quick example. We have these two images here, and I give you a sec to determine which image here is fake and which one is real. And it turns out that the right one was real, and the left one was just purely generated by a GAN network. And you could already see this by this slight distortion on the picture here left. So that was a slight catch there, but we will not go into detail why this happens. But what we will do is we will explore this generative adversarial network, not on the image or video domain, but extend it to the time series domain, and more specifically on the financial time series domain. So we came down to the following research question, which was, can GANs be trained to be a probabilistic model for financial time series predictions? And it is an important note here that we do not want to have a single perfect prediction for the future for a time series, but we want to have like a predictive probability distribution. So we want to plan out different kind of scenarios in the future. So let me first explain a bit more how a GAN network works. And this is an overview of a GAN network, where we basically have two different kind of networks, which are models, which are usually neural networks. So we have a generator and a discriminator, and each have a distinct task. So let me first introduce the discriminator. The objective of the discriminator is just basically a binary classification. So it wants to classify the incoming instances either as a real instance or as a fake instance. And the discriminator is asked to find the distinction between the data samples that are coming from the generator and that are coming from the real data set. And what the objective of the generator is contrary to the discriminator. The generator tries to fool the discriminator into thinking that its generated instances are actually real. So how can a generator learn this? So first, in training, we first give the discriminator a batch of real samples and a batch of generated samples with the labels 0 if it is coming from the generator, and the labels 1 if it's coming from the real data. And in this case, the discriminator knows how to distinguish both the incoming data instances. And at the beginning, at the start, the generator has not learned anything. So it is initiated by random noise, so it just outputs random noise, and the distinction can be made quite easily by the discriminator. But then we update the generator weights by backpropagating the information that is stored in the discriminator to the generator. So basically, what the generator gets fed into is information that the discriminator knows whether this discriminator based its classification on. So the generator will become better and better at replicating real instances, and the discriminator has to improve itself further into making a better distinction between generated and real data samples. So in the end, this generator will be able, if trained correctly, to be able to output images or data instances that are similar to the real data where it was trained on. And if that happens, the discriminator cannot find a distinction anymore, and it will just randomly guess the label it is assigning to. So basically the discriminator will end up as with an accuracy of 0.5. And this looks mathematically to the following loss functions. So we have a min-max game. So we have two, a maximize and a minimization on the loss function. So on the one hand, the discriminator tries to maximize the log probability of assigning the labels from real instances as label 1, and maximize log probability expected value of the instances coming from the generator as label 0. On the other hand, the generator tries to minimize the probability of generated samples assigning as label 1, and tries to maximize the probability of generated samples as classified as 1. So this is the basic GAN setup, and in our case, we wanted to deploy this on time series. So the first simple setup was on sinus functions, simple sinus functions. So the real data contained only one single sinus function, and the training process is explained here. So first you can see that it is just random noise, and it starting to pick up the features of a sinus function, and in the end the generator is able to produce a sinus function, a neat sinus function. So this was still a simple setup. So now we make the data set a bit more complex, and we diversify the data set by varying the amplitude in the data set. So we still have a single sinus function, but we vary the amplitude. And these are some specifications on the training. But the output, as you can see here, is just one single sinus function. And this is a problem because the model is not able to pick up the whole distribution of the real data. It is only outputting a single instance from the data set, and we cannot force the model to increase its variety, because in this instance what it is producing is correct. It is present in the data set, but we cannot enforce the model to also create sinus functions with different amplitudes. And this is in literature known as mode collapse, which is a well-known subject in literature in GAN training. So we had to come up with a more advanced setup to be able to extract the underlying distribution of the data sets. So what we did is we came up with more advanced GAN setup, which is based on the Wasserstein distance. And the Wasserstein distance is a measure between probability distributions, and this is known as the Earth mover distance. So in this analogy, we have two piles of dirt, and we want to recreate one pile of dirt, but with minimum effort. So we want to have two exactly the same pile of dirt, but with minimum amount of effort into turning one pile of dirt into the other. And this is this optimal transport is called the Wasserstein distance. And in this picture, you can see here these boxes here. We want to move the boxes on the left to the distribution on the boxes on the right, and the optimal moving strategy with the least amount of work is indeed the Wasserstein distance between them. And this is the plan that was that's supposed to be optimal. So we move in one box in position 1 to 0.7, and two boxes in position 1 to position 10. Still, the Wasserstein GAN need further advancements. So we created a gradient penalty, which was added to the loss function in order to make sure that the GAN is trained in a continuous space. And I will go into that a bit more deeper in the next slide. And we also added some conditional statements to the GAN. So what conditional statements were the previous time points from a time series. So we can give the GAN the last two or three time points, and then the GAN can predict the following time point from there on. So if we put this all together, we come to the following overview, which is still quite similar to the original GAN setup, but there are some distinct changes made. And one of them is that we do not have a discriminator anymore, but we use a critic. And the critic model here is trying to find a fitting function f. Function f tries to fit to the data coming from the real data set and fitting to the data samples that are coming from the generator. And when we present a batch of samples from the real data set, we apply the function to all these individual samples, and we get output scores for each sample. And we take the expected value from each sample, and this is an approximation of how the distribution of these samples look like. And we do that the same for the samples that are coming from the generator. So we feed in the batch of samples from the generator, and for each instance, we apply it to the function that the critic has learned, and the output scores. We approximate the distribution by taking the expected value of the output scores. And the objective here is to minimize the Wasserstein distance between the probability distribution coming from the generator and the probability distribution from the real data. And if we succeed, then these probability distributions will be equal. So then the Wasserstein GAN is able to find a fitting functions to the real data and to the generator and find the underlying distribution. And that's exactly what we want. We also added conditional statements. So we give the generator some information where it can be base its predictions on. So we concatenate to the random noise the last, let's say, n time points from the time series, and we feed it to the generator. So the loss function is as follows. As I explained here, this is basically the expected value from all the data samples coming in from the real data and the samples coming in from the generator. And we also add here the gradient penalty, and this enforces the function that the critic is learning to be in a continuous space. And this is pretty important to have stable training. So yeah, how can we validate whether the model was actually able to find the function and the distribution of a data set? So we came up with two synthetic data sets. The first one is a sinusoidal data set, which contains sinusoidal functions, different kind of functions with varying amplitudes, frequencies, and phases. And you can see a sample here. And we have an AR data set, which is a data set which contains functions from autoregressive model with two correlated variables, the following function here with the weights given, and we add a epsilon term to each point. So how does the model perform on this data if we present it to the model? The following results can be seen. So from visual inspection, we see here that the sinus functions have a great variety. So that's already improved compared to the last GAN model, where we can see here that the generator is able to make predictions and choose a certain frequency and a certain amplitude, and also stick with it. So, for example, if this generated red sample here, it has chosen to keep amplitude of 1.5, and you can see that that keeps it throughout the whole generation of the time series, which is pretty good sign. And also that we have a lot of variety in the generation now. And the same thing can be said on the samples generated on the AR model. So in red, we have the real samples, and in blue, we have the samples that are generated by the generator. And here we have the first 2 points are the conditions. So these are given to the generator. So the point here, with point 2, is the first point that the model generates itself. And we can see that the path that it follows is similar to the real data, which is a good sign. But we want to investigate a bit further whether it also actually found the right distribution. So we can conclude here that it actually found the function, but also we want to validate whether the distribution, the underlying distribution of the data set was found. So let's evaluate this for the AR data set. These are all generated by the generator after it has been trained. So you can see here that if we condition the first point to be positive, the second point to be negative, if we follow the function where we created the real data set from, the next point must be negative. And this is one inspection that also holds here, so that the generative model is able to pick this feature up. And if we now take all these generated samples and we subtract the function from this, but we exclude the epsilon because we don't know which epsilon the generated sample has taken. So we end up with, for each time point, we have a bunch of epsilon terms, and we can make a distribution of all these samples and compare it with the epsilon terms that we set it to in the real data set. And that's what you can see here on the right. For each point, for this is 4.2, 4.3, we plotted samples of the epsilon term, and we have a high overlap in these distributions. So the real data set has an epsilon term of a normal distribution, variate, and the generated samples also follows the same distribution. So this gives a proof of concept that we were able to first find the function of the data set and also find the underlying distribution. So now this gives great confidence to model this on financial data set, where we do not have control over the function and we do not have control over the underlying distribution. So we need some kind of other metric to validate this. We chosen here to use the ING data on the euro-dollar forex exchange, which is a pretty fast data set where we sometimes have 4 data points per second. We took out a few days, and that should be enough for the training data. So I think this contains 1 week of training data of a price action. So five days, and the test set as well. And we deploy the Wasserstein GAN model on these financial time series, and this gives the following results. So we want to plan out different kind of scenarios. So we do not want to make a single perfect prediction. We want to see whether the model can give different kind of scenarios that could be valid in the future. So what you can see here in the plot is the first 3 points were conditioned. So these are the conditions given to the generator. And then the generator is free to predict whatever trajectory it wants. And this gives some kind of sense of how the probability distribution looks like. So we get a predictive cone with more of high density samples in the middle and less probable scenarios on the outer side of the cone. And this gives a pretty good view of that the generator is able to give really different kind of scenarios. The challenging task now is to find a way to validate this, because we do not have the underlying function and distribution. So we came up with a p-value for p-value distribution, where we take for every time sample, we take the fraction of data samples generated greater than the real sample. And I will not go into the mathematical details, but there is a mathematical derivation that if you take the fractions of all the generated samples that are greater than the real sample, and these are from a continuous distribution. If you sample from that, then you would get a uniform distribution on the p-values. So that's what is shown here. So you can see here, these are the p-values on each time point, and if these are for the higher time points, these are quite uniformly, so that's a good sign. And here you can also see that in the first point it is a bit biased towards generating samples towards the middle and not uniformly. So that was one way of validating this. It's still quite a general check to validate the model. So we wanted to take it one step further. So in this case, we wanted to predict time series that are longer than 30, length 30. So we want to increase the dimensionality of the model, and we have done so by introducing skip connections to the network. So we have these generator and the discriminator model, which are neural networks, and I will not go into detail how these skip connections work, but it gives the ability to a model to choose how many layers it actually wants to use. So for example, we give the model 15 skip connection layers. It can gradually build itself. So it will first use only 2 layers, and if it finds that it needs more complexity, it will add a 3rd layer. And so it can gradually build itself with the model itself. And this gave some pretty promising results, so that we could scale up the time series to 100 dimensions, and this could further be increased. So coming back to the research question, whether we could train a GAN to be a probabilistic model for financial time series, we have covered quite some interesting research, where we first found that the original GAN was not able to reproduce the data distribution of a simple sinus function data set. But we found a proof of concept on the Wasserstein GAN with the gradient penalty on the synthetic data set. So that gave us confidence to deploy it on financial data. And where we have shown that it is a strong performer as a probabilistic generator. We also seen that these skip connections can be used to increase the dimensionality of the Wasserstein GAN. So that's also something that could be done in future work, more extensive research to these skip connections. And one other idea we had was to not only produce an ask price, but also produce a bid price. So we have a multi-dimensional time series generator. So we have 2 time series at the same time. And also what would be very helpful is if we would have a benchmark quantitative validation method for these time series, because this is something that is not present in literature. So this gives it's hard to compare models to one another. So that's something the research space could really benefit from. So yeah, that was my presentation. I hope you enjoyed it. If you have any questions, then I am happy to answer. And if you have any further questions, or you would like to have an insight more on this topic, then you can find me on LinkedIn. Thank you.
Now, thank you, Casper. Your presentation about genetic of synthetic financial time series with GANs has been incredible, and I see that you've been very lucky, because Fabian Jansen has been responding quite to all the questions, but you're lucky because we still got a couple pending questions. So we've got Bouke Brennickmeyer, who wants to know about the GS divergence is the basis of the normal GANs loss, and the Wasserstein 1 distance shows more stable training and less model collapse in practice. So that is preferred.
Yes. Yeah.
Right?
Yeah.
Then the next question is from Ralph. And did you consider decomposing the time series, and it might make it easier task? RNNS, for example, benefits significantly when predicting or decomposed series.
I'm not sure whether I understand the question, but the time series that we chose are we increase the variety of time series by a sliding window in the data set. So we don't, so we have a sliding window over the time series. So that's how we construct the data set. If that is what you intended to on the question, I'm not sure, but I will take a look at the question again.
Yeah, because it's from Ralph. Yes, he's asking another question, Ralph, again, decomposing into seasonal, trend, residual, or other decompositions.
Okay, yeah. So seasonal trends are not included, but that's something that the generator should pick up. But yeah, we all only trained on 5 days. So you could say something like, if we have training data for a couple of weeks, then you could see some seasonality in, for example, that Mondays open, there's a lot of price action. Or even if you take it further to a few months, then you could have the seasonality of different kind of the summer and in the winter. But this is something that is not included in this work now, because the train data was not that extensive yet.
I understand. We have 2 more questions from Hong Pei, and he wants to know about the validation of the model will depends on what you are going to do with the generated data. And
yes, so the generated data can be used, for example, in backtesting algorithmic trading strategies. So if you have an algorithmic trading strategy, you can train it on historic data, but it can easily overtrain on this single time series. So this GAN model, if it is validated properly, then you could use to diversify it on training these algorithmic training algorithms. And it could also be used to data sets that are difficult to share. So, for example, if you have a time series regarding personal health, and one company wants to share with a different kind of company, then you could use these models to train on these time series and share the generated time series instead. But yeah, the validation is still a very interesting topic where more research needs to be done in how can we validate the exact how can we validate whether the generated time series are actually correct. And there are still some you could apply some statistical measures on this, but these I applied a statistical measure on the returns, so the differences on the preceding points, and these statistics are shown that to be very similar, but still the whole time series you cannot really you cannot compare statistically yet.
I understand. And again, a question from Hong Pei. He would like to know if you would like to train ML model with the synthetic data, for example, then you should compare the test results of model trained on the real and synthetic data and test it on the real data.
Yeah, that could be interesting to do as well. Yeah.
Okay.
Yeah.
I see that indeed Fabian had responded to all of your questions, and Ralph was also happy about your answer, and I don't see any more questions coming up. So I would say that if people would like to contact you or get more information from you, you've shared your LinkedIn profile, and also they can find you